So thanks everybody for coming. It's my great pleasure. Today we have two talks. The first one is by Nguyen, and he will talk about the mean curvature flow with surgery in high codimension.
Okay, thank you, Armin, for the introduction. So yes, I hope everyone can hear me very well. I'm here from London, and I'm going to talk today about the mean curvature flow with surgery in high codimensions. So without further ado, I'll just explain the main theorem that I'm going to talk about today. So here, what we are going to consider is a smooth immersion of a closed n-dimensional submanifold with n greater than equal to 8. So here we have Rn plus k, and we will consider here n greater than equal to 8. We can actually go a little bit lower to n is equal to 4, but we don't get optimal constants. And here we will mostly be concerned with the case when k is greater than or equal to 2. So this is usually known as high codimension. So it is not the hypersurface case. But the results do apply for n is equal to 1, k is equal to 1 as well. But there are actually some better results where you can use the special structure of being a hypersurface in that case. And so here, what are we considering is that we consider a submanifold, which is actually just M0, which is cylindrically pinched. So cylindrically pinched here means this particular curvature condition, which is a ratio between the squared norm of the second fundamental form and the squared norm of the mean curvature. And it says that the ratio is bounded below by n minus 2. And usually I make the condition here as well. H is actually greater than equal to 0. Actually, there's a consequence here, but you can put that as separate as well. So here we assume that the mean curvature is strictly greater than 0. And then the result says that we can actually run the mean curvature flow with a surgery. So that will have to be defined later, starting from M0, which terminates after finitely many steps. And a consequence of this termination after finitely many steps is that you know that M is diffeomorphic here to Sn, or a finite connected sum of here Sn minus 1 times S1. Okay, so essentially says here that you can actually decompose the manifold to the objects which you think it is from the condition a squared minus 1 and n minus 2 h squared. Okay, so how do you actually prove a theorem like this? Well, there are quite a few important analytic results to actually prove this theorem. And the first thing what we require here is that I'll explain these later, but here you need a gradient estimate. And what this one says here is that you have a quadratic curvature condition, which is this condition here, a squared minus c h squared. And if this is negative, and if you assume that the mean curvature is strictly positive here, and usually you ask for k is greater than or equal to 2, but it does hold for k is equal greater than or equal to 1. And this constant c, which is here, it works for any c which is less than 4 and 3n. Then what we can show is that there exists a constant, gamma 1, which only depends on n and the initial manifold, and a second constant, gamma 2, which only depends on n and m0, which satisfies the uniform estimate here of grad a squared, gamma 1, a4 plus gamma 2. So here, this is a pointwise estimate. And the key thing about this estimate here is that the grad A, or the gradient of the second fundamental form squared, is bounded at the same point as the A4. So usually when you have a parabolic estimate, you have a parabolic estimate for, or a gradient estimate for the mean curvature flow, but usually what you have to do is take a supremum over A4 over the entire manifold. But for this gradient estimate here, it's a pointwise estimate, so you can compare the gradient of the second fundamental form at the same point and the same time as the second fundamental form at the same point and the same time. And this here is just, it's been written in a simpler way for the mean curvature flow up to the first singular time, but there is a form that actually holds for the mean curvature flow with surgery. So this means that this estimate actually will pass through singular points if you flow with surgery. Now, from this gradient estimate, which is actually the key estimate you require for surgery, you can actually prove a cylindrical estimate. So this is another estimate here. So this is a little bit more geometric. So the first estimate, which was a gradient estimate, which was a more analytic estimate. But here, this is a cylindrical estimate. And what it says here is that if you consider a mean curvature flow, which is a smooth solution to mean curvature flow, which is, okay, compact and quadratically bounded in this form here. So I'm going to ask here for a squared less than or equal to cn h squared. And here, I ask for the constant 1 and n minus 2. Usually we also ask here that h is greater than or equal to 0. Then what we can show is that for all epsilon greater than 0, there exists a lower threshold h0 so that if the mean curvature is sufficiently large, so this h0 is a lower threshold to say that if your curvature is blowing up to plus infinity, well, it should be above a lower bound h0, which is very large. Then what is happening is that the curvature ratio a squared divided by h squared is actually improving. So you can see here that this cn started off with n1 and n minus 2. And here along the cylindrical estimate is saying that if the mean curvature is sufficiently large, then the a squared divided by h squared is actually approaching a better constant, it's becoming 1 on n minus 1 with some small error, which is just an epsilon. Okay, so that's a cylindrical estimate, and it's called a cylindrical estimate because here on Sn minus 1 cross R, we have here that a squared divided by h squared is actually equal to 1 on n minus 1. So that's why it's called a cylindrical estimate, because what is happening here is that you can see that the curvature is actually approaching the curvature of the cylinder, which is Sn minus 1 cross R. And for reference point, if you have Sn, you have a squared divided by h squared is equal to 1 on n. So that's the absolute pinching here. This is the absolute minimum of a squared divided by h squared, because here you have a traceless second fundamental. You look at the traceless second fundamental form, a squared is always larger than or equal to 1 on n h squared. So this, when a squared is equal to 1 on, when a squared divided by h squared is equal to 1 on n, then you're umbilic, and the only compact umbilic surface is actually the sphere, Sn. Okay. Are there any questions? I guess not. Okay. Right, and here, so this what this shows here, this result here, this is the main result, the cylindrical estimate here. This shows at a singular time, a little bit more than that. This curvature estimate suggests that it only approaches the curvature of the cylinder, but actually you can prove more, that if you had at a singular time, then you can actually have an appropriate parabolic rescaling of your mean curvature flow in space-time, so that the rescalings of the mean curvature flow actually converge to a standard embedding here of a cylinder Sn minus 1 cross AB, which lives inside Rn plus 1, which lives inside of Rn plus K. Or possibly you can actually also converge to a sphere Sn, which is an Rn plus 1 inside of Rn plus K. And notice here what we have is codimension reduction. So this is actually quite an interesting phenomenon here, is that in the singular limit, that even though you start off with high codimension, what happens is that as you approach a singular point, you form parabolic rescaling, your codimension drops. So you're actually in a linear subspace of Rn plus K, and actually the linear subspace is actually a codimension one larger than the submanifold that you actually started off with. Okay, so this is actually quite an important point, because of course we know that Sn, the standard cylinder Sn minus 1 cross R, actually lives in a linear subspace for Rn plus 1. So if we want to recognize a neck region in our mean curvature flow, then we will need to have this codimension reduction. Okay, right, so that's actually an explanation of the main results. So here, let me go back and explain a little bit what's happening with the mean curvature flow. So here we have the mean curvature flow. We start off with an F0 with some submanifold of dimension n into Rn here, and we always start off with a compact n-dimensional submanifold of Euclidean space. Then, of course, the mean curvature flow is the following evolution equation here: partial t f xt, and here just notice it's going to be minus h x dot t. So usually, of course, when you're in codimension 1, you simply write here h nu, and you take nu to be the outward normal, and you take h to be the mean curvature, but mean curvature function. But of course here, since we are actually considering a submanifold, and here usually we want to consider here k greater than or equal to 2, so this should actually be equal to k. We're actually considering high codimension. So this mean curvature here is actually properly a mean curvature vector, and it actually has a number of different components. So it'll be a vector of dimension k, it'll have k components. And so actually the flow here means that this actually will be a parabolic system. And this actually makes a very big difference for high codimension minimal surfaces and mean curvature flow. The fact that you actually have a system rather than one equation. And so this is here, just reiterating here, you have the mean curvature vector. Okay, so this is the mean curvature flow. So what is what's the main result in mean curvature flow? Well, here's this is Huysken's convexity result. So this is the result that's pretty much started off the parametric approach to mean curvature flow. So this is from 1984, of course, by Gerhard Huysken. And here you consider a hypersurface, which is uniformly convex. Okay, and then the mean curvature flow has a smooth solution on a finite time interval up to some t max. And here I've written it a little bit loosely. Here, the MTs converge to a round point as t approaches the maximum time interval. So here you have a uniformly convex hypersurface. If you have a uniformly convex hypersurface, you know it's actually already diffeomorphic to the sphere, and the mean curvature flow takes this uniformly convex hypersurface and actually shrinks it. And as it shrinks it, it'll form a singularity with finite time, and at that singular time, that hypersurface will become round. Okay, now what if you relax the convexity result? Well, if you have the 2 convexity here, so this is also a theorem by Huysken and Sinistrari from 2009. You have a smooth, closed, n-dimensional 2 convex.
Sorry, there is a question. What does uniformly convex mean?
Uniformly convex means here, it means more or less that the Hij is larger than here, some epsilon Gij, sometimes, or yeah. Sometimes you put a mean curvature in there as well. So here, Hgij. Okay, well, but you usually, you can actually just ask for convex and compactness. Because here I said uniformly convex hypersurface because I didn't say compact at the same time. I could have asked for convex and compact, or I could ask for uniformly convex, which case it then implies compactness. Does that answer the question?
Seems so, yes.
Okay. Here, so here, I mean, here you have a smooth, closed, n-dimensional 2 convex immersed hypersurface. Here in Rn plus 1, so here you have codimension 1, dimension n greater than or equal to 3. Then you can run the mean curvature flow. What happens with the mean curvature flow? Well, you will run into singularities. So you have to introduce the mean curvature flow with surgery. And then what you can do is actually show that with the mean curvature flow with surgery, that the original submanifold is actually, or here at hypersurface, is actually either diffeomorphic to Sn or a finite connected sum of Sn minus 1 cross S1. And the idea is fairly, well, it's fairly complicated, but it uses this idea here with a mean curvature flow with surgery. And the point is that if you have a closed surface or hypersurface, then the mean curvature flow will run into singularity. So you will have to deal with singularity somehow. If you introduce the notion of being too convex, then you can actually show that your singularities will actually be of cylindrical form or neck-like. So the picture here is actually correct. You have here a mean curvature flow. This is the central picture. If you run the mean curvature flow, you will approach a singular point. So if instead of going to the singular point, what you do is you perform surgery at the neck region. And at the neck region, what will happen is you will remove the neck. And in the middle, you have a high curvature region, which you discard. And then you run the mean curvature flow on the remaining components. And what should happen is that the remaining components should contract to round spheres. So you know, or round spheres, or actually they might actually be cylinders. And so therefore the object has to be a connected sum of Sn or of these tori actually. Okay, so that's the basic idea. Now, what do we want to do? Well, I'm interested in high codimension. So the thing I want to do is actually, I want to generalize these results to high codimension. Now, there's an immediate problem because if you try to generalize Houston's result to high codimension, you need to replace convexity. However, convexity really depends on the fact that the second fundamental form is only in one direction. So if you look at the second fundamental form, it's a 2 tensor valued, it's a vector valued 2 tensor. So in codimension 1, because you only have one vector direction, you can actually turn this this vector value 2 tensor into a proper 2 tensor, and you can ask if this 2 tensor is positive definite. However, if you have high codimension, then the second fundamental form is now only going to be a vector valued 2 tensor. And you can't ask if a vector is positive or not, because that doesn't make any sense. So we need to replace this condition somehow for high codimension. So this is our first problem, even to reproduce Huysken's original result. And so try to understand what's going on. We look at the evolution equations for this second fundamental form. And if we look at the evolution equations for the second fundamental form, here, this is the time derivative. This is the Laplacian, looks good. This term here is the hypersurface terms. They appear if you're in codimension 1, but then you have all these extra terms here, which are the high codimension terms. So if the codimension is 1, they vanish. But if the codimension here is not equal to 1 or larger, equal to 2, then actually these actually appear and they have to be dealt with. So the the evolution equation for the second fundamental form is much more complex in the high codimension case. The evolution equation for the mean curvature vector, here you take the trace with respect to Gij, and here you can see what the problem is here, is that if you take here the evolution equation of the mean, let me put the indices in here. If you have an alpha here, you have an alpha here, but then you have an alpha here. And you can see that if you want to say, for example, show that mean curvature is preserved, positive mean curvature preserved, then what you would require is that the alpha here falls on the mean curvature term. But the index alpha does not fall on the mean curvature term. It actually falls on the second fundamental form term. So from an analytic point of view, you can't actually ask for something like a condition like positive mean curvature. So therefore, it doesn't make any sense also to ask for a condition like convexity in this case either. Okay. However, what you can do is that we can ask for another condition, and this condition actually will be a relationship between a squared and h squared. So here we're going to look at the evolution equation here for a squared and h squared. And here, you can see that it actually has a nice kind of structure here. The evolution equation a squared and h squared, you have a Laplacian term, and here you have a Laplacian term for h squared as well. And what we're looking for is a condition that replaces convexity, but in high codimension. And it turns out actually that a relationship between a squared and h squared is actually going to be the correct condition to replace convexity in high codimension. And actually, what was proven actually here by Ben Andrews, who was my PhD supervisor, and Charles Baker back in 2010, is if you consider here a compact submanifold, which is smoothly immersed in Rn plus k. So here, this can be k, it can be considered greater than or equal to 2, but of course it works for k is equal to 1 as well. And if the mean curvature is not equal to 0 everywhere, and initially satisfies this condition here, that a squared is less than ch squared, with the following condition here: c is going to be less than 1 and n minus 1, or here there's some special conditions here for n between 2 and 3, so it should be greater than 2 here. Then what you can do is that you can show that the mean curvature flow has a unique smooth solution, and this condition here converges uniformly to a round point as t approaches t max. And here, just let me say here, this recovers, well, if here a squared is less than 1 on n minus 1 h squared, and h is greater than 0, then this implies that here, for k is equal to 1, this actually implies that the sigma 0 is convex. So this recovers the original Huisken result with a stronger condition. However, this condition, if you look at it, it actually a squared less than or equal to ch squared, of course, although it implies convexity in codimension 1, it makes sense for any codimension. So therefore, it's a natural condition to consider in high codimension. There's a relationship between a squared and h squared. Okay, and actually what they actually proved is a little bit more, is if a squared is less than cn h squared, and here this cn is can be less than 4 on 3n, so it is not just less than 1 on n minus 1, but here you have 4 on 3n, then this curvature condition is actually preserved along the mean curvature flow. So that's the first thing you actually require to run any kind of evolution equation. You need a good curvature condition which is actually preserved by the flow. Here, so here what we'll do is we consider here this quadratic pinching condition, a squared plus a minus ch squared, where c and a are positive constants. Combine the evolution equations for a squared and h squared, and you get the following. So this quadratic term here. Here, this is a good term here. This is going to be negative. And here you need to control this term here, which is some sort of quadratic nonlinearity. And the quadratic nonlinearity here has this complicated structure here. So this is actually one of the key points. So it's actually much more difficult than the codimension 1 case. In the codimension 1 case, you can see a lot of these terms just disappear, because a minus is actually the second fundamental form in the direction which is normal to the mean curvature. So almost all of these terms vanish, and you're just left here with the terms left over, the first 2 terms, if you have codimension 1. But if you have high codimension, then you have to account for the second fundamental form in directions which are orthogonal to the mean curvature direction, which only appear if you high codimension. And here you have a improved Carter inequality, which relates grad a squared with grad h squared. So if you look at this evolution equation, you can actually show that the terms on the right-hand side are actually negative. So therefore, the inequality is actually preserved along the mean curvature flow. Okay, so that's the first thing you actually have to do. Okay, so here, going back to what I was saying before, for codimension 1, the ratio between the second fundamental form and the mean curvature plus positive mean curvature implies convexity. So therefore, okay, you can see that the theorem of Andrews and Baker is actually a generalization of Huysken's theorem to high codimension, which actually is a restriction of the Huysken's theorem in lower codimension 1. Okay, so what about 2 convexity? So we want to do surgery. So in 2 convexity, the condition that you want to replace is not a squared less than 1 and n minus 1 h squared, but in fact, it's a squared less than 1 and n minus 2 h squared. So in codimension 1, i.e. k is equal to 1, then actually this implies 2 convexity. So therefore, it's natural to ask if we can prove the analog of the Huysken-Sinistrati theorem for this condition, i.e. can we prove there exists a mean curvature flow with surgery in high codimension, and if so that if this initial submanifold satisfies this initial pinching, is the submanifold actually diffeomorphic to Sn, or a finite connected sum of Sn minus 1 times S1. Okay, so let me give you an overview of the Huysken-Sinistrati convexity
Sorry, there is another
theorem.
question.
Yes.
Can you remind me what 2 convexity means?
2 convexity is simply asking here, if you have h, I, j, and it's equal to lambda 1 all the way up to lambda n, then 2 convexity simply says that lambda I plus lambda j is greater than 0 for any I, j. Okay, so that just simply says that if you add any 2 of the eigenvalues, they are positives. That's 2 convexity. Right? It says 2 of the eigenvalues when you add them together is positive, and convexity is just 1 convexity. You take any one of the eigenvalues, that's actually positive. Does that answer the question?
Yes, it does.
Okay. So here we want to prove Huysken-Sinistrati, but therefore we need to look at the proof of Huysken-Sinistrati, and what do we need to prove the mean curvature existence of the mean curvature of surgery? The main estimate is actually convexity estimate. So assuming positive mean curvature, you show that regions of high curvature are actually asymptotically weakly convex. So this is what you start with. You started with positive mean curvature, h greater than 0. Then here, you show that the first eigenvalue here is larger than some delta. There's for any delta, h minus c delta. So therefore, since the delta is arbitrary, we can show as h goes to plus infinity, you can show that lambda 1 is actually becoming non-negative. So it's actually becoming weakly convex in the limit. Now the proof is quite complicated. It proceeds via induction from mean curvature through symmetric polynomials. The second fundamental form, it uses a parabolic form, the Stampaki iteration, the Simon's identity, and the Michael-Simon sublevel inequality. There are simpler proofs now if you assume that your initial submanifold is actually embedded due to proof work by Ben Andrews and Hasselhofer and Kleiner, and also Brian White. But this is the original proof, and this proof actually works even if you're immersed and not embedded. Now, there's no hope of generalizing the proof of this result, because firstly, you have to have positive mean curvature, which doesn't really make sense for high codimension, and the result that you're proving is that you're actually becoming weakly convex, which also does not make any sense for high codimension either. So this proof here is not, this kind of result is not going to be true for high codimension. So we're already kind of stuck if we try to replicate the proof. But a consequence of this proof is the following. It's actually a cylindrical estimate. And the cylindrical estimate says, okay, which and essentially says here that if there's a smooth solution of the mean curvature flow, then actually here you have a squared minus 1 and n minus 1 h squared is less than eta h squared plus c eta for any eta greater than 0. So therefore, here, if the mean curvature is very large, what you're showing is actually a squared minus 1 and n minus 1 h squared is becoming negative as you approach a singular point. And now this is actually a little bit more hopeful to actually generalize to the high codimension case, because it actually doesn't depend on anything which actually only depends on being a hypersurface, because you can't talk about eigenvalues of the second fundamental form for high codimension. but you can talk about the ratio of the squared norm of the second fundamental form to the mean curvature. So this is the kind of result you would like to generalize to high codimension. Okay, in terms of eigenvalues, what it's actually saying is that if you're wondering what this is actually saying, it says that if you have one eigenvalue which is small compared to the other mean curvature, then actually saying that the remaining eigenvalues are becoming close to each other, which is exactly what's happening with a cylinder, because a cylinder has 1, 0 eigenvalue, and all the other eigenvalues are equal to each other. So that's why it's called a cylindrical result as well. And actually, what you really want is actually not even the cylindrical result. You want this gradient estimate. This gradient estimate is the important part to actually imply surgery. So if you have a smooth, closed, two convex initial hypersurface, M0 belongs to Rn plus 1, then what you can show is you show a pointwise gradient estimate for A, where you can actually compare the gradient of the mean curvature at the point xt with the norm of the second fundamental form, sorry, to the power 4, that power is required for scaling, at the same point. Now, because the mean curvature flow is parabolic, you always actually get estimates of this form here, the grad A squared is less than C times a constant times A4, but you have to take the supremum here over the entire manifold. However, this gradient estimate actually is for the norm of the second fundamental form at the same point as the gradient of the second fundamental form, right? Rather than taking a supremum over the entire surface, actually at the same point. So this is actually technically the most important part of this estimate. Okay, and this estimate looks good too, because actually this makes sense for high codimension. So here, if you take an overview of what Huskin and Sinistrati did, it basically a skeleton, what you have is a convexity estimate. This convexity estimate implies cylindricality, and this cylindricality implies a gradient estimate. But in fact, we only want the gradient estimate. This is actually the key defining flow, mean curvature flow is surgery, because this leads to localized curvature estimates. And of course, gradient estimate implies local Harnack inequalities on parabolic neighborhoods. So this is actually what we want. But in fact, what you can do is actually all of these things actually can imply each other. So the cylindricality result actually implies the convexity result, and the gradient estimate actually implies the cylindricality result. So if you can prove either the cylindrical result or the gradient estimate, then you can actually get the convexity result, return the convexity result. So therefore, but convexity result doesn't make sense for high codimension. So therefore, you may as well try to prove the cylindrical result or the gradient estimate. And in fact, they're actually equivalent to each other. You have the cylindrical result, you can prove the gradient estimate, and the gradient estimate, you can prove the cylindrical result by a blow-up argument. Okay, so for high codimension, the convexity does not make any sense. However, cylindricality does, and so do the gradient estimates. So it turns out actually that you can actually just prove gradient estimates directly without actually having to appeal to either the convexity result or the cylindrical results first. And we can prove this gradient estimates first here if we have quadratic pinching, which is just as well, because that's the condition that we have. That's actually the condition that we have. So we have quadratic pinching, and if we have quadratic pinching, we can actually prove a gradient estimate directly. And so this was actually proved in an earlier paper by myself in 2018. So here you have a quadratically bounded solution to mean curvature flow in Euclidean space with Rn plus k, where n greater than equal to 2. Actually, should really say here n greater than equal to 8. Here, then there exists a constant here, gamma 1, and a constant gamma 2, such that the flow satisfies the uniform estimate here, grad A squared plus gamma 1 A4. Okay, Armin, how much time do I have?
20 minutes.
Quarter 2, right? 10 minutes?
20.
20? Oh, okay. All right, so there exists a constant gamma 1 and a constant gamma 2 such that the flow satisfies this uniform estimate here. Okay, and this is actually written here. So I haven't actually introduced the mean curvature flow with surgery yet, and I probably won't because I've always run out of time. But here, this actually is up to the first singular time. but such an estimate actually exists, can actually be continued through the gradient estimate, through the singular times by mean curvature flow with surgery. So you actually always have these points here. Grad A squared is less than equal to gamma 1 A4 plus gamma 2. So here, this is the key result that you need to do mean curvature flow with surgery. And it all follows from here, from this quadratic term here. Okay. And actually, this proof actually is fairly straightforward. Actually, only requires you to use a maximum principle. So you can actually avoid the more complicated use of these symmetric polynomials or Stampaki iteration if you use this quadratic pinching term here. Okay, and what do you do once you have a gradient estimate? Well, when you have a gradient estimate, what you want to do is actually here, you integrate gradient estimates along geodesics. And if you integrate gradient estimates along geodesics, what you get here is that actually you can show here that there exists here constant C hash and H hash, such that if the mean curvature is sufficiently large, then what you can show here is if this HP0 is larger than this gamma H hash for some gamma larger than 1, what you can do is actually you can compare the size of the mean curvature at different points. So this is the main advantages of having pointwise gradient estimates. If you have a pointwise gradient estimate for the mean curvature flow, then you can integrate along geodesics and you actually compare the size of the mean curvature at different points, depending on the distance from each other here, depending on the mean curvature. So what this means is that for the blow-up limit of the flow, it means that if you have a region of large curvature, then in the submanifold, actually what's happening is that you're actually having a large region of large curvature as well. So you don't just get a spike of large curvature, but you actually get a whole neighborhood of large curvature. And this is very important because when you do a blob argument, what you might fear is that you get non-trivial limits. But here, if you have a neighborhood which is also becoming large, comparable to the size of the mean curvature, then when you do a blob argument, then actually the entire region is actually becoming large as well. Okay, so that's a localized High-Nack inequality, and that comes from actually comes from the gradient estimate. And once you have this localized High-Nack inequality, you can actually prove the cylindrical estimate. And here you can prove the cylindrical estimate. So you take here a smooth solution of the mean curvature flow here, where K, of course, is usually greater or equal to 2. And then here you have a compact, quadratically bounded mean curvature flow. So this is the mean curvature flow here. Usually you ask for H greater than or equal to 0, although you can actually show this consequence. Then here, what you show here is that for all epsilon greater than 0, there exists an H0 such that here, this is a threshold, so the mean curvature has to be large. So this is a quantified version of a blow-up argument. So what you would usually do is actually you would take the mean curvature, and you would take the singular time, you would take a sequence of points and times approaching the singular time and singular point, you would rescale, you would blow up, and you would find that you have a cylinder. But here, what this is saying, actually, this is a quantitative version. It says that actually near the singularity, when the mean curvature is sufficiently large, then the curvature of the submanifold at that point, and also in a region of that point as well, is actually asymptotically becoming the curvature of a cylinder, becoming cylinder-like. And you prove this again by the gradient estimate and a blob argument. And you prove that by a contradiction argument with the evolution equation of a squared divided by h squared. And here, so that actually just says here, if you look at this result, actually it doesn't actually say that the submanifold is actually becoming cylindrical. All it says is actually that the curvature of, or the second part, or the curvature of the submanifold is approaching an inequality that a cylinder also satisfies. So it's an estimate which says the curvature is looking like satisfying the inequality that a cylinder has. but that doesn't really say anything about how cylindrical, if the actual region itself where the curvature is large is cylindrical, because that's what you would require if you're going to do mean curvature flow surgery. You would require that you have a region, a sufficiently large region of your submanifold where the submanifold looks like, in parameterization, an Sn minus 1 cross an interval. So at the moment, this cylindrical only estimate only says the curvature is cylindrical, cylinder-like. You want to actually show that a region is actually cylindrical-like, and this is actually the neck detection lemma. And so here, what this says here is, of course, that if you have a mean curvature flow, and here are just some parameters that I can explain later, but these epsilon, theta, L, and K are actually telling you here that how cylindrical like you are. So the epsilon is telling you here is the norm. So there's some norm which says that this region is close in norm to a cylinder. Theta is a time interval, L is the length, and K is a regularity parameter. So it says CK norm, L is the length of the cylinder, theta is in time, how far back in time that the cylinder is that is close to a cylinder, and epsilon is the norm. Then what it says here, that you can find an eta0 and an h0 with the following properties. You say here, this h0 is just saying that this is a lower curvature threshold. So you know that as the curvature approaches plus infinity, it is becoming a cylinder. So therefore, it's saying that if you have mean curvature sufficiently large, and here, this condition here says that h squared is less than or equal to 1 on n minus 1 minus eta0. Now, the previous theorem already tells you that this is actually less than or equal to 1 on n minus 1 plus some epsilon dash here, different epsilon here. So what this is saying, well, if you are less than 1 on n minus 1 plus epsilon dashed, it could be that a squared plus h squared actually could be going towards a squared divided by h squared 1 on n, which means that actually that you are actually becoming like a sphere. But here we rule out that case. We actually say that a squared here divided by h squared is like a cylinder. So it's 1 on n minus 1 less eta0. Then what you can actually do is actually show that the neighborhood here is actually a shrinking neck. So this actually tells you here that not only is your curvature becoming cylindrical-like, but actually there's an entire region of length L backwards in time, in a time interval theta, where the entire part of the mean curvature flow looks like a shrinking neck. Now, once you have this, you're in good shape, because now you actually know you can have regions where you can do surgery. If you have those regions where you can do surgery, then you can actually run a mean curvature flow with surgery. Okay, so that's the main part, the existence of these cylindrical neighborhoods. And this is called the neck detection lemma. Okay. Okay, and so now I'll just outline the surgery procedure here, because actually it's quite complicated and there's lots of parameters that you have to do. And there's a very complicated procedure where you actually have to do the surgery by hand. So here, once we have the neck detection lemma, we know that if you have regions of high curvature, then you know that you have regions which are close to cylindrical necks. And these cylindrical necks are of the form Sn minus 1 cross R. Once you know that, you're actually in a position to implement surgery. Again, the surgery procedure is quite complex. Just let me outline the main points. Here, surgery, what it does, it replaces a portion of a cylinder, Sn minus 1, times a small interval AB, with, at most, 2 spherical caps. Okay, so now, we have to understand that surgery here is not really reverse connected sum. It actually may not make the surface topologically simpler. What it's doing is actually detecting regions of high curvature, and then it's cutting out regions of high curvature. It cuts out regions of high curvature so that you can actually continue the flow, because regions of high curvature are bad for the flow because they force the flow to form singularities. So therefore, the surgery actually cures an analytic problem and not a topological problem. So you actually may be performing surgeries in the flow which actually do not topologically simplify the surface. Okay. By the neck detection lemma, this surgery takes place at points of uniformly high curvature, and the surgery procedure then reduces the curvature by a uniform amount here, which by removing disconnected components of high curvature. Okay, so in the middle of the neck region, you do possibly two surgeries at either end, and in the middle is the region with high curvature. And then you have to prove, okay, this is called the neck continuation theorem, which I haven't actually outlined here, but you prove in that region, which you will discard after the surgery, that that region actually has the region with high curvature. And so just to point out here, the surgery doesn't actually make the submanifold topologically simpler. And here, the last point is the surgery terminates after finitely many steps. Okay, all right. So actually, I've gone a little bit faster than I thought. Usually, there are lots more questions. But okay, so I'll just stop here, and I'll see if there's anyone want to ask any questions.
So, thank you very much. Are there questions, preferably via the microphone?
I've killed them all.
So if there's no other question.
So I ask one question. So
Sure.
somewhere you have the dimension n larger than or equals to 8. So why
Yes.
is this 8?
It's because in the evolution, because here, if you have you have the pinching C of it. Oh, wait, stop. Sorry, the pencil is dead. Okay. No. My Apple Pencil is not working.
Oh, it's okay. It's okay.
Okay, the reason is, so the reason is because if you have the curvature pinching condition, I'll just say you have C of n is less than 4 divided by 3n. Okay, but you need the curvature pinching is actually, that's the curvature pinching that is preserved. But the optimal curvature condition, which is for the cylinder, is 1 on n minus 2. Okay. And you can see for n is equal to 8, that those two are actually equal. So here, when you have n less than 8, you have to have a less than optimal curvature pinching, which is actually, you replace the curvature pinching with, instead of 1 on n minus 2, you replace it with 4 divided by 3n. So that's the reason.
So this is not related to this 8 in the singularity of the.
No, there's nothing. There's not. That's the reason that it appears.
Okay, thanks.
It appears because
yeah.
that's the best pinching that you can preserve.
Thanks.
All right. Any other question?
Okay, can I ask something? On this last slide, you say there is, you replace it by at most 2 spherical caps, could be 1 or even 0. In the 0
Yes.
case, that doesn't seem to make sense for me.
I mean, if you have Brian White's, so here you would have like a very strange, like two bowl solitons, coming together, and so that just simply collapses within finite time. So that's what it means to 0. I mean, that's a very special case, and generically won't happen. Okay, that's the only reason it can happen. Of course, you can have 1. I mean, what I mean here by 1 is actually when you the 2 spherical caps means that you cut and then you cap both sides, and you could do that twice. So technically, you would actually have 4 caps. It means 2 surgeries. You can also have 1 surgery because you can have a degenerate neck pinch. If you have a degenerate neck pinch, you only do 1 surgery, and then you have what I haven't discussed about here, which will actually be quite another long talk, would be the neck continuation theorem. Actually says that if you in the situation where you only have 1 surgery, actually that's the other side of the surgery is actually convex. So the object you have in the middle is actually a sphere. Topologically, you know what it is, so you can throw it away.
Okay, thanks. Yeah.
All right. Any other question?
I have a question. Maybe this is very elementary. You said capital A was the second fundamental form, and then you had
Yes.
also small letter h. Is there a difference, or?
Oh no, just in some papers I use H, and some papers I use capital A. That's all.
Okay.
It's the same.
And then you had these results with norm of A and norm of mean curvature, and you pointed out always that when you have something like that, the mean curvature is small, then you have that, and then you said the curvature of the manifold is small. Does that mean that the norm of the second fundamental form is bounded
When
by...
I say no, I usually when I say that, I say when the curvature is large, the mean curvature, which bit. So I usually say if the mean curvature is sufficiently large,
yeah,
then usually the statement is something along the lines that you have that the ratio between a squared and h squared is bounded by 1 on n minus 1 plus epsilon. So that is becoming more cylindrical, as it were.
I see. And then does that, so this ratio, the norm of A divided by
h squared, yes.
Does that have anything? So why is it called curvature? I mean, of course the mean curvature is in there.
Yeah, because you can write down the whole, you can write down the Riemannian, all the curvature, because it's a submanifold. The Riemannian curvature can be written in terms of the second fundamental form.
Ah.
So therefore it is all of the curvature.
I see.
Okay, then the curvature pinching condition says, you know that a squared is bounds h squared, but the curvature condition says also that a squared is bounded by h squared. So if you bound h, you bound a. If you bound a, then you can bound all the curvature. And that this means the curvature, this means the Riemannian curvature of the submanifold, but it also means the normal curvature of the normal bundle.
I see.
So that means it controls everything.
Right. Okay. Thanks.
Further questions, remarks, comments? If that's not the case, let's thank Hui again. Press my button.